Terribly sorry if I just shared all of my political beliefs and opinions with you. Won't happen again. That's not a funny one to do because I could get in trouble for that maybe. Do you guys know where I stand politically? Good, you shouldn't. Do you know where I stand religiously? Good, you shouldn't. Do you know my real name? Good, you shouldn't. All right, nope. No, I'm messing with you. It is Kyle. All right, for this, now that it's worded more clearly, I want to give you guys a couple seconds, or minutes rather. I want you to solve this one. Okay, I'm gonna pause it. I want you guys to check it out, set up your knowns. We now are with air resistance, which means do we get to use that final velocity we just found? Not quite. Now, I'm going to give you a guiding question. You do not have to write this one down, but I want you to consider the following as you're setting it up. What does constant velocity, because that's what it is, it's constant velocity once that parachute's open and stuff. What does constant, weird, velocity imply? This should be the driving question behind your setup. I'm going to give you guys a moment or a couple moments. I'll come around and see what you guys are doing. Cool. I'll give you a little bit of time. So, coming together, I'm going to draw a free body diagram first. The first thing I care about, Nick, I loved your answer, but I want to see if anybody else can get it. If I say there's constant velocity, what does that mean with regard to forces? There's no acceleration. The only way that you can have no acceleration is if the forces are completely balanced. Otherwise, there'd be a force pushing somewhere. Now, with no acceleration, if we look at the picture of this, here it is. Gravity pulls this thing down, right? Now, no acceleration means no net force. And I'm going to use better language. Zero acceleration means zero net force, which means if this is the force of gravity pulling me downward, what fights the force of gravity for this crate that's falling through the air? The drag force, right? It's the air resistance on the parachute that opens. If there's a net force of zero, these things must be exactly equal in magnitude, but opposite in direction. Because we're not accelerating anymore, this must be the case. If gravity wins, you speed up downward. If drag wins, which it won't, you would speed up upward, which would be a super weird thing to see happen if you drop something out of a helicopter. Okay, so let's check it out. We know a few things. I'm going to write it like this. Because the acceleration is 0 meters per second squared, this implies to me that the net force is equal to 0 newtons. That is a really important idea. Okay, beyond that, we don't really have any other knowns, I suppose. We still know the mass. I don't remember what it is. 415 kilograms. And we are trying to find in this problem the force of the drag from the parachute. Okay. Have I lost anybody yet? And let me rephrase that. What questions do you have at this point in the problem? Bet. All right. What are we trying to find? Drag? Gosh. Okay. Super important question. I need every single person here to be able to answer this. Maybe not right this second. I hope right this second. But if not now, in 5 minutes, if I ask the same question, or tomorrow or next week, you better answer this question. How do you find net force? Okay, I heard lots of murmurs. I heard forces. What else? So we'll get there. You're absolutely right. Check your notes. We made a comment, and I'm trying to see where it would be. All right, it's in 4.1 under the bullet combining forces. It's a big definition, I think. So we talked about contact forces, field forces, agents, free body diagrams with all those guidelines, and then we talked about combining forces. We said that net force is the what? The sum of all forces acting on an object. What are the two forces acting on this? So before we get there, just the forces. So I have the force of gravity plus the force of drag. Okay. Now, if we just plug in, because I know that this is 0, this is what my statement reads. The force 0 is equal to the force of gravity plus the force of drag. And I'm likely showing more work than you would. But can we solve that for the force of drag? What should I subtract from each side before I do any mass and acceleration stuff? Let's subtract the force of gravity. And we'll write it like this. So negative the force of gravity is exactly equal to the force of the drag. Okay, equal but opposite. When we do this, let's just find this force of gravity. And maybe I should include one more known here, because Nick, now's your time to shine. To find the force of gravity, you take m, mass, times what? Okay, here's the weird part, and we're going to need another known. What do we have written as the acceleration? 0. Now, when we're finding the force of gravity, this is Newton's second law, we use ma if it's just like an accelerating object and we know its mass. What was the other format that we used, though? Weird. The other format. G. What's G? Negative 9.8, and it's not meters per second squared. How do we write it? Newtons per kilogram. Okay. I'm going to make a little note to myself. Okay. So mg, negative mg is the force of the drag, right? And then I'm going to swap these around. F drag then. It's negative, what's our mass? .415, and that's kilograms. And negative 9.8 newtons per kilogram. What happens with the kilograms in these units? They gone. Gosh, we're left with newtons, which is a force. I don't know the number, but 415 times 9.8 is going to give us loud, Abigail.
4,067.
Can somebody second that? Okay. What are we going to make sure to do with every single example? Statement. The parachute produces how many newtons of drag? And I don't need you to just read it. I can see it. The parachute produces 4,067 newtons of upward drag force. Notice we take the need for any positive for negative by just using the language upward. Okay. Through this problem, this strategy, we saw it, I believe, yesterday when we were looking at the, I'm trying to remember the example that we did. We did an example where we had to set up the net forces like this before. This is going to keep happening. It happened with the tension in the cable problem, is the one where the same thing happened. This idea of net force is going to be super duper useful. Okay, questions about this problem? We're almost done with the section. I'm going to give you time today to work on some homework stuff. Any part of this that you look at and go, nope, I didn't get it, and it's 5 minutes later and I'll ask my question now. I should not throw in that little snarky comment if I want you guys to speak up. Mental note. Doable? Good catch. All right. Oh. Because how do you find force according to Newton?
Mass times acceleration.
And if we're talking about weight, we call it the force of gravity instead.
Yeah.
And G is just the gravitational strength due to gravity. You could call it the acceleration due to gravity as well. We just use G to make sure it's clear that we're talking weight. Cool. Good question. All right. This random thing. I want you guys to sketch not sketch, on your right margin somewhere, write a capital N. And I wrote one just now that felt odd, and I'm curious. Here's option 1. Here's option 2, where this is 1, 2, 3, or 1, 2, 3. Which one do you guys go with? How do you draw your ends? Do you start with a vertical line going downward? You go upward? I do this, down, and then I do this. But just now, when I do this and I do it fast, oftentimes it winds up like, it's not going to do it now that I'm thinking about it. A lot of the times it winds up looking kind of funny, and I'm seeing if I have an N anywhere. Yeah, I get this double loop because I go down and up. And then just now, randomly, as I was doing the problem, out of nowhere, I decided that this is probably the more efficient way to do it. Weird little thing that I just noticed out of nowhere. Cool. Thank you for indulging the randomness. All right, so we have one more little statement to make. All right, now, the idea that we were approaching with this, it turns out that maybe everything that we essentially deal with on our planet has drag force. Like, even as we walk through the air, remember, I'm feeling drag. Anybody in here ever skydived? All right, so quick question. We probably won't have it in meters per second. If I jump out of a plane, theoretically with a parachute, but without it would also suffice for this kind of thought experiment. I start speeding up, right? Which means if I jump from 10,000 feet, I'll reach a pretty high speed. Any idea, roughly, how fast a skydiver will fall? Like, right before they pull the parachute. Any guesses? Let's go miles per hour, because that's probably more natural for everybody. Faster. Faster than 100 miles per hour. Little less. It's between 150 and 170, typically. Now, bless you. Skydivers do or do not have any control over how fast they go? I think they do. There's a difference between whether I fall like this, with my arms completely spread out, or if I fall like this and point my head down like I'm diving, right? What's the difference? The air resistance, and let's use more common language, or more physicsy language. The drag is different. The larger the surface area, the more drag that you get, right? Now, as we go through this, let's say after 10,000 feet or 8,000 feet, they reach a speed of 150. If we jump from 20,000 feet, what do you think their speed is going to be? Twice as high. The same. Why? Oh, love it. Okay, how many of you guys have heard the term that Rafa just referenced, terminal velocity? Okay, so we are going to define it. This is the last little part of our section. We're going to define for ourselves terminal velocity. And look at that N. Weird. All right. When you see the word, terminal, what does it mean? Okay, and you do what at the terminal? Like, you've gotten on at your gate, you get in the plane, and then you terminate your trip, right? Like, that's where the word comes from. This is the very last stop. So terminal is just a fancier word for final. If you have an object that's falling through the air, or through any fluid for that matter, there's going to reach a point where you don't speed up anymore. There's still gravity acting on you, but inevitably drag is going to eventually cancel out that acceleration that's due to gravity. So as we look at this, we're going to say that by definition, this is the constant. I'm going to underline that part. The constant velocity. An object achieves, and I'm going to say an object falling through fluid, falling through a fluid, the constant velocity an object falling through a fluid achieves when, and I'm going to write this kind of mathy, and maybe I don't have to, we'll do it both, when drag force equals gravitational force. Now, we are looking at one thing because gravity pulls down, drag does what? It pushes up, right? So notice I didn't account for the signs there. I'm going to write this underneath just in the in a nicer way. Velocity when the force of your drag is exactly equal but opposite to the force of gravity. Now, couple different things that happen here. If I ask you to ride a bike with a parachute tied to the back of it, like, it's tough to start, but you can do it. And if you can ride a bicycle, I bet everybody in here could ride pretty comfortably at like 5 miles per hour. Okay, the parachute would be inflated to be pulling behind you. If I said, okay, go 10 miles per hour instead, is it easier, harder, or the same amount of difficulty? Harder. What if I said go 20 instead? It's still harder, right? Because as you pass through this fluid that we call air, when you're going faster, you're passing through more fluid, right? More air that you're traveling through, which means more air to push back on, the force increases. So a couple statements that we're going to make just about these things. As an object speeds up, I'm going to change color here. As speed increases, what happens to the drag? It increases. And I just want to show you guys, if you're in my pre-calc class, notice as velocity approaches infinity, the drag force will also approach what? Infinity. Look at this end behavior that we can just tie right in with that idea in pre-calc. Neat. Okay, other things. There's a few different pieces that are going to impact this. Could you jump off a 20-story building and be fine? No. Can a bug? Depends on the bug, but typically yes. Why? So what if we do drop a bug that doesn't have wings? That's a great point. I think it's still going to make it. Like, it'd still probably be okay. What's different between us and a bug? Like, there's lots of differences. But with regard to physics, what might be the biggest difference? The mass. Now, mass doesn't impact how quickly you accelerate, right? Because acceleration due to gravity is 9.8 meters per second squared, no matter what it is. However, the force of gravity is directly impacted by mass, right? You weigh more the more mass you have. So we're going to make a little comment. We're just going to note that larger areas, larger surface area with, and I wish I could write italic, I don't know how, low mass have, how do I want to word this? Larger surface areas with low mass have lower or smaller terminal velocity. And I'm going to go way out on a limb here, but I think you'll be able to make sense of it. There's my shorthand for terminal velocity, V sub terminal. Okay, the more heavy an object is, the less that the size is going to matter. If I drop a 50-pound bag of concrete, it's going to fall about the same speed, realistically, as a 500-pound bag of concrete. When you're at low masses, this is much more impactful. Okay, especially through fluid like our air. All right, so couple things. If you have a skydiver falling like this, your book refers to it as spread eagle, but I don't like that terminology. You'll see it in a question. About 60 meters per second is how quickly a skydiver will fall at their terminal velocity on our planet. If I were to drop a ping pong ball, faster, slower, the same speed as a human being? Because they're so much lighter, right? Okay? Ping pong balls, no matter how high you drop them, about 9 meters per second. Okay, that's a pretty quick run. If you drop a basketball, it'll fall a little bit faster than ping pong. Do you want these numbers? Do you want me to write these down? in case you want it, common terminal velocities of just a few objects. And then you guys are going to have about 15 minutes. So common v terminal. I'm just going to say Earth. All right, person. And obviously it depends on the person, but we're working with their arms out, 60 meters per second. Okay, ping pong ball. Approximately 9 meters per second. Okay, a fully inflated regular sized basketball. About 20 meters per second. And the last one that I'm going to have is a baseball. I think a baseball is lighter than a basketball. Would you agree with that? What do you think its terminal velocity is going to be? Higher or lower than a basketball? Higher, even though it's lighter, right? Why? So its density is certainly higher. I would say its surface area is significantly lower. Okay, a baseball, maximum approximately 42 meters per second. You guys ever heard the thing that if you toss a penny off the Empire State Building, it kills somebody? That's not true. Terminal velocity of a penny is not enough unless it like hits the soft spot that should be cleared up by now on most of you. Maybe if you dropped it perfectly on somebody whose soft spot wasn't cleared, it might kill them. But realistically, no. Terminal velocity is too light to reach a high enough terminal velocity. Cool. You guys get the next 15 minutes to work on, and I'll go do it here. Okay, so today, and I'll just come here, you get the privilege of homework 4.2.2, which you will find on page 105. I want you to do 22 through 26. Okay, this will be due tomorrow. When you're working through this, very intentionally be mindful of writing down your knowns, your find, and your equations. Get in the habit of doing that with a contextual answer when appropriate. 10:15. Physics lesson. Terminal velocity. All right. Cool. Pre-calculars that missed the quiz, would you like to continue working now?